Hey, Liam.
Oh, hey, Dr. Steinhauer.
Hey, I'm hearing you in real time.
Oh, look at that.
That's neat. What a cool thing.
It's like it's working.
It does seem like it's working much better. Hey, everyone, welcome back.
That looks and sounds great.
Yeah, this is way better.
Okay, that's much better. Great. Sometimes you just have to shut everything, when in doubt, shut everything down and turn it back on again, and sometimes it'll just work then. Okay.
I've been that now. And
Excellent. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I think we're even almost here, all here. Okay, so to recap what we were trying to talk about just before we left, I posted an article for Friday's class. Friday will be Astrobytes Day. I'll have a 5-10 minute presentation ready to go at the beginning of class. Your job is to read the article and be ready to come with your questions and be ready to discuss it. So that's how this will work, and how it will work every week. So by Wednesday, whoever is doing the Astrobytes for Friday, I'll need your article so I can post it by Wednesday. I'll probably make a page and just post all of the Astrobytes with the schedule so that we can post links there. And there's a one place where you can go every week and see where that's being posted. Okay, great. Let's get back to it. So we left off talking about parallax, and we did the thumb experiment, and we were talking about how this works in astronomy, where we have a much bigger baseline, but we're talking about much bigger distances that we are interested in measuring. So this geometry is important. We're going to come back to it in a minute, but first let's get some handle, because parallax is something that's built into your brain. You're tuned to understand parallax. To see how that works, let's see a couple of examples of it. Here is parallax, where we're moving back and forth from different vantage points of objects on a virtual table, and you can tell immediately, your brain knows which ones are in the foreground. You wouldn't even need one to pass in front of the other one to know which one was in the foreground. The ones that are moving the most have to be the ones that are closest. That's, your brain intuitively understands that. And parallax is no different. Here it is. Here is actual parallax of stars. Here is the Orion constellation with the 3 belts and Betelgeuse and Rigel and Bellatrix and Safe, I think. Here's the Orion Nebula. Anyway, the important point of this animated GIF is these are showing actual parallax motions of stars exaggerated by a factor of 1,000,000. So if all of these stars were 1,000,000 times closer than they are right now, this is actually how they would appear to move over the course of several years as we're moving them back and forth. And again, your brain, you can almost see the depth in this field. Your brain automatically makes it happen. Those things that are moving fastest, furthest, are the things that are the closest to us. So it's no different in astronomy. We just need to take very careful measurements to be able to identify any of these actual motions in the sky. Okay, so let's go back to this. I'm actually going to stop this share and open up another share. Let's see how fast I can do this. All right, not too shabby. So this is where we're at, and this is the geometry that we've got. Now, there's a couple of weird things. All of this is weird, but the important thing here is that as we identify stellar parallax, P is the parallax angle here, this guy right here. And you'll notice the weird thing is it's not the entire angle that the star appears to move. So again, when we're in 2 different locations in 6 months apart, a star will appear in 2 different places in the sky. And you can measure that angle, the angular difference between where that star is in one point at time of the year and 6 months later. That total distance is twice what we're going to call the parallax angle. right? So the parallax angle is exactly half of the total distance that those stars seem to be moving. Depending on where they are in the sky, actually, they'll either do straight lines, or they'll do perfect circles, or they'll do some sort of elongated ellipse, actually depending on whether they're at the celestial equator or the pole. If they're at the poles, they do, actually it's not the celestial equator, it's the ecliptic equator, and because it's the motion of the Earth around the sun that matters. So that's neither here nor there, but it is the major axis of that ellipse that we're talking about. And P is really the semi-major axis of that ellipse. So when you talk about a parallax angle, you're really talking about half of the total distance that the star seems to move along the major axis. Why do we do it that way? We do it that way so that we get this triangle, where one of these, we know that, so we got a right triangle now. Here's our right triangle. And we know that one side of this is P, and we've got now one side of this is D, and one angle is P, and we've got our right triangle solved. We're interested in knowing the distance, and we know the P, and we also know one other, distance on this triangle. What's that?
Distance from the Earth to the sun.
The distance from the Earth to the sun. That's exactly right. Which is what? It's one if you
exactly 1 AU.
units. It's 1 if you use the right units. That's exactly right. This is 1 astronomical unit, which is probably the worst named unit in the history of units. Because if you didn't know what it was to start with, its name gives you zero idea about what it is, other than something to deal with astronomy. But it is, in fact, the semi-major axis of the Earth's orbit about the sun, or if you like, the average distance between the Earth and the sun. And since the Earth is on a pretty circular orbit, pretty much always the distance between the Earth and the sun. So this gives us a right triangle, which is we can do some trig on now. So let's give myself some whiteboard space, and let's bring my notes over here so I can actually see them, and so I don't make any silly mistakes. So here is that triangle that we just drew. This angle is P, this side is D, and this side we know is 1 astronomical unit. By the way, one of the reasons why we do half the angle is to make this side of the triangle 1, because who wants to divide or multiply by 2? That's just hard. So tan of P is 1 AU over D. For very small p, we know that tan P is about equal to P, and we have, this is an extremely good approximation. Every single parallax angle that we've got is extraordinarily small, and this approximation, really, you don't even have to use the approximation symbol for. That the errors that you bring in with using that approximation is completely insignificant compared to any errors that you're going to introduce from anything else. So you can just make that an equal sign and you're fine. So we can make this is just equal to P. And then we can solve this for D, because the distance is really what we want. D equals 1 astronomical unit divided by P, the parallax angle. Now, in doing this approximation, though, we have specified what our units on P is. What are our units on P?
Astronomical.
Good guess, Hunter. That is not it.
Arc seconds?
Good guess. That's what we want to get to, but making this approximation only works with P in a single unit.
Oh.
And it's not arc seconds. It's got to be radians. This only works. In fact, this is how radians are sort of built, so that tan P is equal to P. So this is really in radians. And that's not what we want, because radians are a really big unit of angle. And we're talking about really, really small units of angle. And so unless we want to go around and every single parallax number we ever write down is a number that's, 10 to the minus 7, that's not going to be useful. So we need a smaller unit of angular measurement to measure P in, and Sarah had it bang on, the arc second. So what the heck's an arc second? Let us add another page here. The one thing I don't like about this program is that I can't just scroll infinitely and get into the whiteboard. I have to actually make a separate page. So I'm moving back and forth between these things. Anyway, that's neither here nor there. So we like arc seconds. Not only because, well, I mean, it's kind of a cool unit anyway, but it is a useful unit for parallaxes because the biggest of them are on the order of that magnitude anyway. So what is an arc second? There are, of course, 360 degrees in a circle. There are 60 arc minutes in 1 degree. So the single dash is an arc minute. You'll see it written both ways, but this is a way easier than writing arc seconds. And of course, there are 60 arc seconds in 1 arc minute. And this is an arc second. So it works very similar to minutes of time and seconds of time in that there are 60 minutes is a 60 division of the big one, and then seconds is a 60 division of 60 of the minutes. So how many arc seconds are there in a radian? This is actually a number that every astronomer knows. So you'll know this. I mean, I'm not asking you to memorize this number, but you'll end up knowing it by the time it's all over. So we know that there are 2 pi radians in a circle and 360 degrees in a circle. So 1 radian is 360 degrees divided by 2 pi, which is 57.2958 degrees. And then if you multiply that by 60 and then by 60 again, you get the number, which is, anybody know it?
206,265.
It's 206,265. Exactly right. Proud of you, Sarah. 206,265. 206,265. With some, that's plenty of digits. Arc seconds. So that's how many arc seconds there are in a radian. And that is a useful number to know because this number gets folded back into the parallax formula because we want to express our parallax angle in arc seconds and not radians, because it's just going to be an easier number to work with. So let's go back to this formula, D equals 1 AU over P parsecs. I'm going to add another page and write that formula again. 1 astronomical unit divided by P. I'm going to call this PR for parse. PR is the parallax angle in radians. And we're interested in having that be PA, the parallax angle in arc seconds. So we know that PR is going to be a lot smaller of a number than PA, right? So PR equals PA divided by this 206,265 number, right? So PA is PR times 206,265. And if we plug this back into there, we can do this in terms of PA instead. So distance in this case will be the 206,265 comes up. We get 206,265 astronomical units over PA. But that's also a rather messy formula. And astronomical units really isn't the best unit to be measuring the distances to stars in any way. It's a much better unit of measure for measuring things around the solar system. So to make our lives even easier, and astronomers are inherently lazy, so let's make our lives easier, we define another unit, which is equal to 206,265 AU. in fact, we define 206,265 astronomical units to be what? Anybody know what we call that unit?
Parallax.
Light year?
It's a parsec. You've heard the term parsec before. This is how it's defined, 206,265. And that makes this formula really easy. D equals 1 parsec divided by the parallax angle in arc seconds, or just 1 over P if you know what units you're talking about. And this is why it's called a parsec. If you have a star whose parallax angle is exactly 1 arc second, its distance will be exactly 1 parsec. Parallax angle, arc second, parsec. That's how the word is defined, and it's how the distance is defined. So a parsec is defined to be the distance that a star would be whose parallax angle is exactly 1 arc second, or whose total distance moves as 2 arc seconds in the sky, because the parallax angle is half the total distance. So that's a lot of, well, it's not a lot of math, but it's some math to get to a very simple equation that even intro astronomy students can use fairly easily, with the understanding that this distance, if you plug in, the only way this formula even works, plug in parallax angle in arc seconds, get out distance in parsecs. There's no other really way to use this formula unless you do some crazy unit conversions, which nobody ever does. We just talk in parsecs and we talk in arc seconds, and everybody's happy. Now, how big is a parsec? This is a lot of AUs, 206,265. How does it relate to some other units that you might know? 1 parsec is about 3.26 light years. So this is bigger than a light year, this particular unit of measurement. And it's a useful one for objects that are in our solar neighborhood, that are excuse me, stars that are in our solar neighborhood. Okay, what is the closest star to the Earth, to the sun? Obviously, the closest star to the Earth is the sun. The next closest star, though, is a star called Proxima Centauri. Centauri, because it's in the constellation Centaurus, the Centaur, and Proxima just meaning closest. So Proxima Centauri is actually part of a triple system. There are 2 stars which are fairly bright, that orbit one another fairly closely, one of which is basically a solar twin. It's almost exactly the same mass as the sun, and fairly rapidly. And there's a 3rd star that is much further out and much smaller on a much longer orbit. And it happens to be in their orbits the closest of these 3 triple star systems to us at the moment. And I think that this one's on a long enough orbit that it's sort of like thousands of years before it's not going to be the closest one to us. And one of these other 2 will be the closest one to us. So it will be the closest to us for our lifetime. So that's just an interesting factoid about Proxima Centauri, the closest star system to us. But how close is it? What is its parallax angle? The parallax angle of Proxima Centauri is 0.77 arc seconds. And that, again, is the closest star to us. All other stars are further away from that and therefore have smaller parallax angles. And so not even the closest one. So an arc second is not a bad unit of measurement, right? It's about a number about 1. But even the largest parallax angle has a parallax of less than 1 arc second. And all the other ones, of course, the further away you go, the smaller this number gets. So how far away is it? Becomes one pretty easy now. Take 1 over P, 1 over 0.77 in arc seconds. This is in arc seconds. You get 1.3 parsecs or 4.23 light years. which is the distance to the nearest star system. I do a intro astronomy a scale model of the solar system, and in that scale model, it's actually, if you've ever been to Washington D.C. And walked along the National Mall in front of the National Air and Space Museum, there is a scale model of the solar system actually built up on there. And in that model, the sun is about the size of a grapefruit. It's about this big. And it's a 10 billion to 1 model, scale model actually. So in that scale, the sun is about the size of a grapefruit. The Earth is the size of a ballpoint at the tip of a pen, 15 meters away from the grapefruit, right? So that's the scale that we're talking about. And it's useful for understanding the solar system and how far things are away. On that scale, where the sun is a grapefruit in Washington, D.C., the Alpha Centauri system is in San Francisco. All right, it's another grapefruit-sized thing, or a few grapefruit-sized things in San Francisco. So that is the closest system to us. Almost all of space is completely empty. Even in the solar system, right? The sun, grapefruit, 15 meters away, that's a lot of empty space. But that's just peanuts to what's out there in terms of interstellar space. And that's just peanuts to the intergalactic space. But I'm getting carried away there. Okay, the fact that that stars are so far away, though, caused some problems in early times, right? The Greeks understood the concept of parallax. They understood that, hey, if the Earth is moving around the sun, we should see the stars move. They should not be stationary in the sky. And the fact that they couldn't measure these differences and changes in the stars is one of the things that led them to believe that the Earth was at the center of the universe. And that's and even 1500 years later, when Tycho Brahe was making the best measurements that had ever been done with his giant observatory that was dedicated solely to measuring the positions of things in the sky, he looked for stellar parallax and could not find any, and concluded that the Earth must be stationary and at the center of the universe, and devised a completely crazy model. This is after Copernicus had come up with his sun-centered model, realizing that made all of the observations much easier to explain. Tycho Brahe came up with a model where the Earth is fixed at the center and the sun goes around the Earth, but all the other planets go around the sun. So it causes problems when we know that this stuff should be happening and we can't measure it. In fact, it was not until 1838 that anyone successfully measured the parallax angle of any star in the sky, right? That's how far we have to go before we can actually measure this stuff. It's important, right? Finding distances to things is important to understanding everything else about them. And this is the only geometric way we have of determining distances to things outside our solar system. Every other method of determining distances relies on this method to calibrate it, 1, and 2, it relies on some theoretical understanding of the objects that you're talking about. Either standard candle, assuming you know how luminous they are, or standard rods, assuming you know how big they are. Every single other distance measurement relies on this and is not geometric, relies on some sort of theoretical assumptions. So this is still really important, and it's getting more important by the day, because in modern times we have some very ambitious projects whose sole purpose is to measure parallax angles of stars. So modern this is starting to be modern. The Hipparchus satellite is the first satellite that really was launched whose dedicated mission was measuring parallax angles of every single star in the sky that it could see. And it was impressive. This is in 2007, so it's already pretty old and it's already way out of date, but this is impressive anyway, and it's useful to know the history. Hipparchus measured the parallax angle of 118,000 stars, and the parallax angles were good to about 0.001 0.001 arc seconds. That was the 1 sigma uncertainty on the parallax angle of these objects, which is pretty amazing, right? That's a milli-arc second, right? So we don't believe, you know, if Hipparchus reports a parallax angle of 0.001, we don't believe it because the uncertainty is 0.001. But by the time you get to 0.003, you've got a 3 sigma result, and you start believing that. So there's believable parallaxes in 2007 that are good to 0.003. And that gets us out to, so again, believable parallaxes of about 0.003, which gets us to, you know, d1 over p, about 300 parsecs. Away. We believe parallaxes angles from this thing out to about 300 parsecs. So that's pretty good, and it's way better than had ever been done. This is like a factor of 10 better than any parallax measurements that had ever been done before. But it still wasn't very good, right? How does this look on the galaxy, right? Here is a scale model of the galaxy. Looks something like this. We're about 2/3 of the way out on one of the spiral arms. This is a side view of it. Obviously, if you're looking down, you see spiral arms. Does anybody know how far it is from us to the center of the galaxy in parsecs?
Is it like millions?
It's not millions of parsecs, no. It's thousands of parsecs. It's about 8 kiloparsecs. So it's 8,000 parsecs to the center of, you know, roughly about to the center of the galaxy. So if we were to draw a diagram around the sun that Hipparchus opened up knowing distances to, right? That's 300 out of 8,000. That is not even 10% of the way there, right? You're talking about a dotted line that looks like this, something like that. That's the extent of the stars in the universe and in our galaxy, which we had parallax, which we had, you know, any parallax angles for. And by the time you got out to the edge of this, you know, your uncertainties were about 1/3 as high as the number itself, and you know that leads to a 30% uncertainty in the distance itself, right? So even at the edge of this disk, you're not really getting all that good at distances. So that was good. It was way better than ever done before, but the room was there to significantly expand and make this better. And that room was filled by the next mission that came along, which was the Gaia. I'm still red. I'll do this in red because Gaia is that important. The Gaia mission, which launched in, I don't know, the mid-teens, 2015 maybe, something like that. And they've had they've been taking data now, maybe even before that, 2012, 2013. They are going to do 10 times better than Hipparchus did, or maybe even 100 times better than Hipparchus. It's staggering how good this satellite is. And they've already done 2 full data releases, and they've done half of a 3rd data release now, actually just in December. So let's talk about data release 2, because it just changed astronomy and changed our research and everything that we do. It's kind of amazing. So this, I'll say DR2, what I really mean is data release 2. And this is only 5 years worth of Hipparchus data. It's a 15-year mission or a 10-year mission or something. I don't know. I'm probably getting these numbers wrong. But it's a small fraction of the total data that they're going to have at the very end. Hipparchus, remember 118,000 was pretty good for Hipparchus. Gaia has reported measurements of, this is April 2018, 1.7 billion stars. It's a staggering number. That's a 10 to the 9. It's 4 orders of magnitude more stars than Hipparchus had. It's stunning. Current precision, I won't say current because it's not current anymore. as of December, this has changed. It has DR2 had precisions of about 50 micro arc seconds. And that's really what Gaia is pedaling in now, micro arc seconds. Micro arc seconds. I'm not even talking about milli arc seconds. I'm talking about micro arc seconds. 50 times 10 to the minus 6 arc seconds is the uncertainty on these Hipparcos, on these Gaia parallaxes. It's crazy. This is already a factor of 20 better than Hipparcos. There was just a month and a half ago in December, the early data release 3 came out. It's about the same number of stars, but they have it's now including more measurements, and they've beaten this number. I haven't gotten official word from Hipparcos, but estimates are that this number is about 30% lower than this number. So probably in the order of 30 to 35 arc seconds, micro arc second accuracy on the EDR3 with a similar number of stars. The final catalog, so this was released in December. I think the final catalog is scheduled to release in 2023 or something, but has the full data in it. Let's say this is better by about 30%. Final catalog. For the brightest stars, they claim I'm gonna define this for people who know what a magnitude is. Less than 10, say. Precision of about, they're hoping for 7 micro arc seconds, which is staggering. To put that in perspective, 7 micro arc seconds is the angular diameter of a human hair at 1,000 kilometers. A human hair at 1,000 kilometers will subtend 7 micro arc seconds. I did some Google Maps stuff yesterday, just how far away is 1,000 kilometers? Peoria, Illinois is almost exactly 1,000 kilometers from us. So a human hair in Peoria, Illinois has a angular size of 7 micro arc seconds. That's how accurate this thing is going to be. It's staggering. Fainter stars will have slightly worse parallaxes, obviously, but that's not really the point. The point is it's pretty amazing. So here is, oh, this is my other. This is the Gaia satellite. You should go and look it up. It's crazy. This isn't just taking pictures of the stars. It's actually constantly streaming and spinning and having stars drift across its pixel frame and measuring them as it goes. It's really complicated, and it's pointing in 2 directions at once, so it can constantly be making comparisons of stars that are 90 degrees away. And this is how it leverages. I don't understand the magic that it does, but it's able to do this somehow. It's also not in Earth orbit. It's orbiting at L1 or at L2 actually, the Lagrange point that is further away from the sun than the Earth, and it's orbiting the Lagrange point and doing its magic out there. Oh, there it is, 2013. It launched on 2013, December 19th, 2013. There you go. What else? So this is Gaia's reach. Again, this is the disk of the galaxy, drawn in non-cartoon version. This is the bulge of the galaxy. This is roughly where we are. Again, this dotted line was where Hipparcos could go, right? This, I haven't looked at this thing in a while. Gaia spacecraft. Right, so everything in this window will be accurate within 10%. And everything in this will be accurate to, oh, proper motions. Ah, right. we have to talk about proper motions in a bit. That's actually how stars are moving through the sky. So parallaxes to the galactic center, better than 10% accuracy, stunning, and proper motions that are accurate out to even the far side of the galaxy. It's a stunning achievement, and it's changing completely the way we're doing astronomy these days. Okay. We'll talk about other ways to get distances later. Obviously, you need to be able to get distances to other things. We'll talk about standard candles and standard rods later on. But let's talk about something else that's weird in astronomy related to light, and that is stellar brightnesses. So, how do we measure brightnesses of things? And this is section 3.2 in the book, the magnitude scale. Okay, so brightness, you know what brightness is. We've talked about brightness in other physics classes. It is energy per second.
I can't help you with that on Apple Watch.
Wow, stop it, Siri. It is, so so how do you measure brightness? It is energy passing through some aperture per second. So usually has units of like joules per second per square meter or something. That's a brightness. A luminosity would just be, joules per second. But we're talking about brightnesses, measuring brightnesses of things. That's not how we do things in astronomy, though. And this, the problem in astronomy is that it's the oldest of the sciences, and so we're stuck with some things that are literally ancient in terms of convention. And this is one of them, the magnitude scale. So the story goes that there was a Greek astronomer by the name of Hipparchus. And by astronomer, we just mean people who watch the sky, because there were no telescopes or instruments really to measure anything other than using your eyes. But Hipparchus, after whom the satellite is named, actually, made the first real catalog of all the stars in the sky, right? He wrote down the positions and brightnesses of every single star in the sky. It was a stunning achievement. It had thousands of entries, or at least over 1,000 entries. And, he was just using his eye. So he was saying, yeah, that one's brighter than that one. Yeah, that one's brighter than that one. Yeah, that one's brighter than that one. So he put them into bins, right? He said the 20 brightest were rank 1. And the next group of brightest stars he called rank 2. And the next brightest group after that he called rank 3, all the way down to rank 5. And so this was the standard, right? For the astronomers that came after him, including Ptolemy, who did his epicycle thing that got published in the Almagest, used this as a reference because it was useful, because you could refer to stars and talk about stars that you could see in the sky. And so everyone that came after that sort of used this as a reference guide. And it wasn't really, you didn't really need anything else quantitative until photography becomes a thing, right? Even once telescopes are invented, you're still just comparing brightnesses of stars that you see in your telescope, right? You have no way to quantify it. It's all going through your eye. But as soon as photography becomes a thing, now all of a sudden we can take an image of a star field and we can actually say, well, I actually know that this star is 3.5 times brighter than this star because I can measure its relative brightness on the screen, on this photographic plate that I put in my telescope directly. And at that point, you need to have some sort of quantitative way of handling these brightnesses. Well, people had been using this magnitude scale for so long that they didn't want, you don't want to totally destroy that system, and so they didn't. And so in 1856, when you first started to need a quantitative scale, there was a guy called Pogson who defined the magnitude that sort of quantified Hipparchus's scale in some weird way. And so, so this is how the magnitude scale came to be. It was defined by somebody in the 1800s, but they were only using it so that Hipparchus's scale would kind of be preserved in some numeric way. And so here it is, the magnitude system. That's the story of it. That's why we're stuck with it. Here it is. I'm gonna write down an equation and then we'll talk about what it means. M1 minus M2 equals negative 2.5 times the log of B1 over B2, where this is a log base 10. I'm gonna write the 10 here, but I won't in subsequent iterations of this formula. Pretty much every time I write log, I mean log base 10. And every time I write ln, I mean log base e. So I will stop writing log base 10, but just know that all of these logs, pretty much that I'm gonna be doing, astronomers love log base 10. It shows up everywhere. So what are these things? M1 and M2 are magnitudes. And B1 and B2 are brightnesses. Brightness. These are, I'm almost out of time. These are what a normal physicist would use for the brightness of things. These B1s have units of joules per second per square meter. That is the normal sane thing that anybody would do. These guys have no unit. They're simply called magnitudes. And this is a weird system, right? So one of the weirdnesses, there's a couple of weird things about the system. The first is that it's a log system, right? It's not a linear system. It's a log-based system. And that's sort of because our eyes are logarithmic, right? Our eyes are logarithmic to give us a huge dynamic range. We can handle seeing very, very bright things and we can handle seeing very faint things because our eyes process things in a logarithmic sense. So this log preserves Hipparchus's, this was a by eye way of measuring brightnesses of things. The negative sign though is the kicker, right? This scale is backwards, right? The brighter the star, the smaller the magnitude. And that's just gonna take some, if you're not used to that already, it takes some time to get used to. This is a backward scale. The smaller the number, the brighter the star. And the weird thing about it also is that it's only defined as a difference in magnitudes, right? You need a 0 point. The 0 point is not defined by the scale. You need a 0 point. So once you define your 0 point, then you can define the brightnesses of all the magnitudes of all the other stars in the sky. And the 0 point that we define is the bright star, which is up for the Northern Hemisphere people in the summer sky, is the bright star Vega. Vega is defined to have magnitude equals 0. And then once you do that, it's one of the brighter stars in the sky. All the other stars, almost all the other stars will be positive, which is nice. There's a few stars which are brighter than Vega, which are negative, but that sets the scale. All right, we'll talk more about the magnitude scale. I'm out of time. And also, move on to other things as well on Friday, including astrobites. So don't forget to read the article for Friday. I've just posted the link, and we'll pick this back up on Friday.
Have a good one.
Maybe technology will work better then. Who knows?
Thank you, Doctor.
Bye.